Hello, fellow mathematicians in Algebra 3. We're in Lesson 28, and we are going to start off with something relatively easy. It's called factorial notation. We did it maybe one lesson there at the very end of Algebra 2. We didn't spend a lot of time on it because it's relatively easy. It's fairly simple to go through. And on top of that, there's a button on your calculator that does it for you. We're just going to kind of go through the process of understanding it, and we're not really going to use the calculator just yet until we understand exactly what factorial is and all the parts and processes of it. Then once you get that, then we can start using the calculator a few lessons down the road. All right, so factorial notation. So what that means, or what that looks like, I should say, is if I have 4 with an exclamation point, this exclamation point means that is the factorial. That is what you would say when you see that, right? 4 factorial. And all that means is you're going to do this. You're going to start with the number 4 and multiply in descending order until you get to the factor of 1. Whatever number it gives you, that's where you start. That's all it is. So 4 factorial would equal 4 times 3 is 12, times 2, that would be 24, because we know times 1, it still stays the same. So the 4 factorial is 24. All right, easy peasy. And that's all it is. There are a few things we can do with a factorial. So let's just jump in and start with these practice problems. So I want to evaluate in 28.1, I want to evaluate, I'm just not going to write that whole word, 5 factorial. So that means I'm going to say 5 times 4 times 3 times 2 times 1. 5 times 4 is 20. 20 times 3 is 60. 60 times 2 is 120. Times 1 is still 120. That's it. That's 5 factorial. It's 120. And it's always 5 factorial is always going to be 120 because the factors of it does not change at all. So let's look at how to evaluate something a little bit more complex. Without a calculator, we are going to evaluate 9 factorial divided by 3 factorial times 5 factorial. All right, so we'll start by simply writing out the factors and just make it easy on ourselves. So our factors are 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, right? Now we have 3 factorial times 5 factorial, so that's 3 times 2 times 1 for this one, times 5 times 4 times 3 times 2 times 1. So now what do you think we did? If you said factor out or cancel the common factors, you would be right. So this whole string right here, 5, 4, 3, 2, 1, we can factor it out entirely. Those are gone. Now we can look at what's remaining and see if there's anything else that we can factor out. And I know that 3 times 2 is the same as 6, so we can get rid of the 6 as well. So now what we have is 9 times 8 times 7 over 1. So our factorial is going to end up being just these numbers times each other over 1, which would be a whole number. So I know that 9 times 8, that's going to be 72 times 7. So that's 14, carry 1, that's 4950. So the answer to the problem is 504. So we can evaluate something like this without having to do a whole bunch of big multiplication by understanding the components of the factorial and that we can factor some things out of there. Let's do one more. I think we might have one or two more. Let me clear this. 28.3. Again, I said this was going to be really easy and your brains needed a break anyway because we're going to do something hard very shortly. So here is 28.3. We're going to evaluate 14 factorial divided by 6 factorial times 11 factorial. Same process. But we're going to take a shortcut. Instead of writing all of this out, we're going to stop at 11. So this is how you can shorten the process. So on top, we would have 14 times 13 times 12. And then, I don't know why it does that to me. Let's rewrite that, 12. And then the 11 would get taken away when we factor out this 11 below it, right? So we don't even have to write that. The only thing we have left is our 6 factorial. So that would be 6 times 5 times 4 times 3 times 2 times 1. Right. So here's something I see. Excuse me. I see some factors that I can get rid of. For instance, I know that 12 is the same thing as 4 times 3. So I can factor those factors out and get rid of them. And I know that 14 is the same as 2 times 7. So I can factor out that 2 as well. So now my factors remaining are 7 times 13 over 6 times 5. That's all I have left. So I can quickly multiply that, and I'm going to get 7 times 10 is 70 plus 21. So it's 91 on the top, and that's 30 on the bottom. 91 is a prime number. I can't do anything with that. So that would be my final answer. Easy peasy. We have one more. And we are going to, let's just do it right here, 28.4. This one asks us to evaluate this factorial, 11 times 10 times 9 times 8, on the calculator. We're going to use our factorial key on the calculator to evaluate that. Now, we really don't have to, but it just is trying to teach us how to use the calculator. So that's what we're going to do. We're just going to pull that up, and we're going to look at this. So here is your factorial button. You should have something that either looks like an exclamation point or X with an exclamation point in order to do that. So what we're going to do, what we have to see first is that we're missing the number 7 after here. So we would think about how that would work as a factorial, right? So what this would be, this could be 11 all the way to 1, and then underneath you would have written 7 factorial and then factored out everything behind the 8, all the 7 factors and all the 7 factors to make this over 1. Can you visualize it? If you can't visualize it, this is what we did. 11 times 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1 over 7 times 6 times 5 times 4 times 3 times 2 times 1. And then we factored these out. And that's what we had left. So we have 1 here. So it's over 1. Or it's a whole number. So this is what it's asking us to imagine in order to solve this on the calculator. So we pull our calculator back up, and we are going to rewrite this as 11 factorial divided by 7 factorial, because that's what this is, right? We have that sequence there. That's what we can do with it. If I can get my calculator to come up here. There we go. All right, so on the calculator, we're just going to type 11 factorial divided by 7 factorial, which equals 7,920. That's a little bit faster than multiplying all of these together. So that would be 7920. Don't forget the 9, Tracy. And we can double check that. So 11 times 10 would be 110, and 9 times 8 would be 72. So that would be 220. 770 would be 7920. So they match. So this works. When you see this sequence here, and you know that the next number behind that would or could have been factored out if it had started down here below, you can just plug into your calculator 11 factorial divided by 7 factorial, or whatever that first number is, divided by the factorial that's missing, and that will give you your answer. All right? Okay, so let's move on to the hard stuff. So we're going to look at some abstract rate problems. And by abstract, I mean we're not actually solving anything. We're using variables. That's what makes it abstract, because we can't put our finger on an absolute value. We're just going to rearrange some letters. So I'm going to put this first problem up here, and I'm going to, well, I'll tell you what, first, before we do that, let's talk about, we're going to go back to our original, we had the distance equals rate times time. That's what we started with. And then we briefly talked about distance could be a job, that rate times time could equal a job. And then we threw another variable in there, and we said that you could also factor it as rate times time times the number of workers could equal the job. These are good things to have in your back pocket. Write it down in the back of your notebook. But we are going to go right back to this one first. And instead of always solving for distance, sometimes we need to solve for rate. So in order to solve for rate, we have to rearrange this right here. And that's good practice for what we're going to be doing in just a moment. So we have to take the rate and realize what the relationship is with time. It's multiplication. So if we want to solve for rate, we need to factor out the time. So we're going to divide both sides by time, which means that rate is going to equal distance over time. Same thing for time. Sometimes we need to figure out let me go back to the beginning here. We need to figure out what the time is instead of the rate or the distance. So we would do the same thing. We do the opposite thing. We would factor out or divide by the rate in order to get time by itself. That would cancel. So time can be written as distance over the rate. So you can see we can solve for distance by multiplying the rate times the time, right? Or we can solve for rate by dividing distance by time, or we can solve for time by dividing distance by the rate. We can extrapolate those formulas from this original formula pretty easily. We just have to take whichever variable we want to solve for, move the other one underneath distance, and divide that by that distance by that value. So it's pure algebra. It's still following that logic that we are used to, and it follows all the rules of mathematics and inverse operations that we understand and know and love dearly. So now that we've explored that, let's jump into our first rate problem, and I'm going to pause and write it up here so it doesn't take up too much of your time. All right, so here's our problem. The train traveled m miles at p miles per hour and still arrived 1 hour late. How fast should the train have traveled to arrive on time? So we're going to begin. The first step is to identify the original values of rate, time, and distance. So our original distance is what the train traveled, and that is m miles. So our original distance is equal to m miles. Okay. Our rate that it traveled is here. It traveled that distance at this rate, p miles per hour. So the rate, I think I'm going to write it over here, just to make it easier. The rate is equal to p miles per hour. And the time, which we know is the distance divided by the rate, we take the distance and we divide it by the rate. So I'm going to say m miles divided by p miles per hour. And in order to simplify that, we're going to multiply the top and the bottom by the miles per hour here in order to solve. We're gonna calculate that out. So we're going to multiply the reciprocal hours per miles here, and then hours per miles here, because it's the reciprocal of this. The miles here would cancel. This cancels this. This cancels this. So that rate is equal to m over p hours. That is the time. Okay, that's where we came from. So we just wanted to simplify. That's why we did all of this right here. So m over p hours. Distance over rate is the time. And it makes sense that the unit of measure remaining would be hours because that's the length of time, right? All right, so I'm going to erase all this and move this back over here so we can see it a little bit better, so we have more room. So to arrive on time, the train will have to travel the same distance in 1 hour less. So the new distance, the distance is the same distance. So there is no new distance. The distance remains the same. Okay, so the new information though, we're going to make a list of the new information so that we can adjust our time for this train, or the rate for the train, I'm sorry. The distance remained the same, so it's still m miles. That doesn't change. But we've got to adjust the time because it's 1 hour late. That affects our time. So we have the new time is going to be m over p minus an hour. And that's going to be in hours. That's our new time. Here it was m over p. Now we need m over p minus 1 in hours. That's our new time. Okay, so that is going to give us our new rate. Now, this is kind of complex, and we usually don't like to have this as a time. We want to have it more succinct. Just like we did here, we're going to simplify this. And the way we would simplify that is by multiplying 1 to get the common denominator by p over p, right? So then what happens is that this p it becomes p over p. So then this becomes the time is equal to m minus p over p, because they both have the same denominator now. We can put them in one fraction, and that's in hours. So now this is just a little bit more succinct. Okay, so now we can find our new rate. And our rate is, again, up here, our rate is equal to distance over time. And we have it. We have the distance, and we have our new time. All right, so that's what we're going to do. Our new rate is going to be the distance of m miles over m minus p over p in hours. All right. Now, in order to get this simplified, we are going to do the reciprocal, just like we always do. So we are going to flip this and multiply. So we're going to do it to the top and the bottom. So we're going to multiply this by p over m minus p, right, by hours. And then this is going to be times p over m minus p in hours. And this allows, this cancels this cancels this. And imagine, if you will, I'm going to take this and move it up out of the way. This right here we turn that into a fraction and put it over 1 so that we can do the multiplication, right? So what happens is this p multiplies by this. This hour cancels this hour. And what we have left over is MP, is M times P, miles from here. And this hour stays in the bottom. M minus P, and the hour stays in the denominator, hour. So MP over M minus P miles per hour, if that makes sense. Okay, that is our new rate. So you can see why they're called abstract, because we don't actually have a value that we can solve. There's no numbers involved. It's all letters being moved around the board, which is kind of crazy. Let's do one more like this, just so we can make our brains hurt a tiny bit more. And you know, if you need it, I have Tylenol. So let's clear the page. Let's do one more of these. If we go slow and we take our time, it's not so bad. We just have to think about it. Trying to rush through these types of problems, it's just going to mess you up. So take your time. Go fix you a cup of coffee, get you a loaded tea. You might need the extra caffeine to keep you awake until the end of the problem. But breathe, relax, walk away, come back, you know, think it through, revisit it next week. You know, take the time that you need to fully understand what's going on, and just one at a time, one step at a time. Okay, I don't know if I told you this or not, but take it one step at a time. So let me put 28.6 up here. All right, last problem. The boat traveled K miles. So K is our distance. Our distance is K miles in T hours. So that's our time. Our time is T hours. And was 40 miles short of the goal when the gun went off. If the skipper tried again, how long would it take to reach the goal if she increased the rate of travel by 10 miles per hour? So the first step is to identify the rate, time, and distance of the first trip. So we have the rate, we have the distance, we have the time. Now we need to figure the rate. And we know that rate is equal to distance over time. So the rate is equal to K miles over T hours. That's our rate. In the next trip, the new distance, we have to add 40 miles to what she can do within that time period. So our new distance is going to change. Our distance is going to equal K plus 40 miles. That's our new distance. Because she was 40 miles short this time, she needs to go 40 miles more the next time. So that means that's our new distance. That makes sense. And the rate will be 10 miles per hour greater. So she's also increasing the rate by 10 miles per hour. So our new rate is going to be K over T plus 10. We gotta get 10 faster. So we're going to, and that's in miles per hour. So we need to get this a little bit more simplified. So we are going to, again, multiply this by T over T so that they both have the same denominator. So our new rate is actually K plus 10T over T, and that's in miles per hour. All right, so that's our new rate. So let me erase this old one and bring this up. Or it's not the old one, it's the one we used to solve to get the new rate. We had to kind of figure it out a minute. So we have our new distance and we have our new rate. And now how long would it take? That is our time that we're looking for. That's what we're trying to solve for. So we know that time is equal to distance over rate. Right? So that's what we're going to do. Time is equal to the distance of k plus 40 in miles over our rate, which is k plus 10t over t in miles per hour. So now I'm going to take the inverse and multiply the top and the bottom. So times t over k plus 10t miles per hour. And then we would do the same thing here. And I'm going to do the same trick that I did last time and just move this up, right? And make it over 1. And then I'm going to multiply by the reciprocal here. So t over k plus 10t miles per hour. Okay, and so here, oh, that should be miles. I messed up. So here we have this miles cancels this miles. This miles cancels this miles. This hour cancels this hour. It could be either one. Either one of those would work. So now we have this k plus 10t cancels this, and this t cancels this. So what we have left is this here. So our time is equal to k plus 40 times t over k plus 10t, and that's going to be hours because that's the only unit of measure we have remaining. Does that make more sense? You find this, the original stuff, you find the new information regarding the question that we've asked, and then you use what we know about time and rate formula in order to fill in the blanks with what we know. So here time is equal to distance over rate, so we take the new distance, the new rate, and we just do some abstract multiplication of variables and get as much of a resolved final answer as we can. I mean, that's all we can do. And that is the final answer. And that is also the final problem for lesson 28. If you have any questions, please ask, and I will see you in lesson 29.